Hello, welcome to Mechan 2040 Solid Mechanics. I am Globus. The topic for today is the direct stress due to bending. This is the fourth tutorial, so it will cover the content in week 4 and week 5. First, we will do some review of basic structural analysis, which is taught in Mechan 2020 Statics and Dynamics. Besides, we talk about sign convention of beams under the pure bending, as well as the technique of how to draw the shear and bending moment diagrams. Besides, we will introduce the most important topic of this chapter, which is the Flexure formula under the pure bending. In tutorial 0, we talk about the first moment of inertia. In this tutorial, we will talk how to find the centroid of a cross-section by using the first moment of inertia concept. Apart from that, we will also introduce the design considerations. Let's first do some basic review of structural analysis. In the structural analysis, there are a lot of supports. As you may see in your previous course or in this course, there are some supports that you should bear in mind with. There are 3 kinds of supports which are very important. One is the roller support. The roller support provides only force in vertical direction. An example in the daily life is the curtain rail rollers with the hooks attached. On the rail of your curtain, there is a roller support like this. And if you hang your curtain on it, the roller support is under an external load P pointing downward caused by the curtain. Consequently, this roller support will drag the curtain upward. In the beam analysis, the typical roller support is like this. For a simple beam, there is a pin as well as a roller support, and as you can observe, the roller support has some wheels under it. That means, therefore, it will just provide a vertical force. Next is the pin. Most of you might be familiar with what is a pin in the structural analysis, but you may not really understand what is the difference between a pin and a fixed end. Typically, a pin provides only force in any direction. Why I say only? Because in the structural analysis, not only force, but also moment will be taken into the consideration. Pin provides only force in any direction. That means for this force, it can be decomposed into the orthogonal components. A typical pin in the daily life is like this. A pin is fixed at the floor, and it is the nut. There is a bar like this, and for this bar you are free to rotate about this pin. For a fixed support, different from a pin, a pin only provides an arbitrary force which can be decomposed into orthogonal components. But apart from the arbitrary force, the fixed end also provides a moment which prevents from this bar from rotation. So still remember that for a pin, the bar will be able to rotate freely about it. But for the fixed end, the bar is completely fixed and no rotation is allowed to be performed, as well as the translation, of course. Another very common support is the simple support. Suppose you have a pin and you place this bar onto a table. Then for this table, it will provide 2 forces. One is the vertical component, of course. Another one is the horizontal component. For the horizontal component, it has often come from friction. If the table is completely smooth, then there will be no such horizontal component occur in this problem. Let's solve some very basic structural analysis problem. For problem A, it is a beam with fixed end A under 2 external forces acting in different positions of this beam. one is in the middle at an angle of inclination of 60 degrees pointing downward. Another force is acting on the tip. It is pointing upward with an angle of inclination of 30 degrees. Their magnitudes are 50 kilonewtons and 20 kilonewtons respectively. You are required to find the reaction force and the reaction moment at this fixed end. Besides, a beam with fixed end A and the roller support C is subject to a loading in the middle as shown here. If AB equals to BC equals to 1 meter, you are required to find the reactions at A and C. For the first problem, first, sketch the orthogonal components of forces as well as the moment at this fixed end. By our equations in statics, we know that the net force in x direction is 0, meaning that AX plus PB cosine 60 degrees minus PC cosine 30 degrees equals to 0. Also, the net force in y direction is 0, meaning that AY minus PB sine 60 degrees plus PC sine 30 degrees equals to 0. Apart from that, we also consider about the moment, about point A, but we know that when PB is decomposed into orthogonal components like this, then the horizontal component will provide no moment to this fixed end. The vertical component will provide the moment with the arm AB. Similarly, for PC, if we decompose it into orthogonal components, it will have horizontal and the vertical one. Similarly, the horizontal one does not provide any moment, but the vertical one will provide moment with the moment arm AC. Therefore, we can write MA plus PC sine 30 degrees AC minus PB sine 60 degrees AB equals to 0. This system should be easy for you to solve. The answer is shown here. You can verify it yourself later if you have time. For part B, it has a 50 kilonewton force acting in the middle at an angle of inclination of 60 degrees. Similarly, we draw the orthogonal components at the pin A, as well as the vertical support force Cy at point C. Solving for the net force in x direction, net force in y direction, and the moment about point B, actually you can take moment at any point you like on this beam, but taking the moment at point B is just for ease of calculations. Consequently, solving this system, you will have those answers. It is left to you for checking. Now let's talk about the sign convention of beams in the pure bending. For pure bending, first, let's talk about the sign convention of moments. It should be easy to see that, as you can see, for positive moment, it will generate you a positive mood. That is, you will smile when the moment is bending your mouth. Similarly, a negative moment will bring you a sad, negative mood, and you will have a sad face when the moment is bending your mouth like this. So if we talk about the moment inside a beam which is cut in pieces, then actually you can see how our sign convention works. When considering a piece of material which is cut, then you can see this material is separated into the left section and the right section. At the right hand end of the left section, the sign convention will follow the moment at the right hand end of this beam. Similarly, for the left end of the right section, it will follow the sign convention here. You can see their correspondence like this. You can see their correspondence like this. Similarly, for the negative moment, it is like this. You can see their correspondence. Next, let's talk about the sign convention of shear load or the shear stresses. Consider a stress element located in between the two sections. For this stress element, recall our sign convention concepts in previous tutorials about the stress elements. It should be positive if there is a positive force acting on the positive surface of it. So for this piece of stress element, it is in positive shear. Then the result of the positive shear is transferred to the beams. That means for a beam cut like this, if you are analyzing the moment and shear stress on this side, then the moment is like this because of our smile, and the shear force is positive if it is pointing downward because it comes from this. So similarly, for the right section, first we try to bend it to smile like this, and then for the shear force, it is positive when it is pointing upward. It comes from the stress element located in between them. Similarly, for a negative shear stress, there is a negative force acting on the positive surface. Consequently, these two results are transferred to the beams so that we define the sign convention of beams under pure bending. Next, let's talk about the shear and the bending moment diagrams. Actually, there is not so much things to talk about how to draw the diagram, because unless you do some example, there is no way you can really understand this concept. So in this tutorial, we have two problems related to the shear and bending moment diagrams. The following example will be an easier one, while another example at the end of tutorial will be rather complicated and for you to challenge. So let's introduce an example on how to draw the shear and the bending moment diagrams. Sketch the shear and the bending moment diagram of this simple beam. The length is 2 meters and it has a distributed load of 500 Newton per meter. Firstly, we have to find all what we know from statics. The statics tells us that RA equals to RB equals to 500 Newton. It is very significant because it is distributed load across the whole length. Now we cut the beam at an arbitrary location X. Then we consider the forces on this tiny section. First, RA equals to 500 newtons. Besides, there is a distributed load 500 Newton per meter for a length of X. So this length is X. Now we are going to find the equation of shear force and moment on this end. Still recall our sign convention. You cut this section here and you have this left section and the right section, which is not drawn in this problem. For the left section, on its right hand side, the sign convention of shear force and moment is like this. For moment, you are bending it to smile, or for shear force, you are pointing downward. Then you can find the equation of shear force and moment in terms of X. For the shear force, by the force equilibrium, the forces in the vertical direction is 0, means that Vx plus 500 Newton per meter times x meter minus Ra equals to 0. Consequently, we can write Vx equals to Ra minus 500 Newton per meter times x meter. Then Vx equals to 500 minus 500x. Next, let's consider the moment in this beam. For this piece of cut material, the distributed load has a moment center located in the midway. The magnitude is 500x. Now we take the moment from this end. Then Ra is generating a moment of Ra times x, while the distributed load will generate a moment of 500x times x divided by 2 in the opposite direction. Then we can write mx equals to Rax minus 500x, which is the magnitude of the distributed load, times x divided by 2. Now we have both Vx and mx. Then we simplify them to get this result. Next, we can draw our shear and bending moment diagrams by using those two equations. So for this equation, it is linear. At x equals to 0, it is 500. At x equals to 2, it is minus 500. Then you can just draw this straight line like this to get this shear force diagram. Besides, the moment is actually a quadratic equation. Recall that the axis of symmetry of a parabola is given by minus b divided by 2a, which equals to minus 500 divided by minus 500 equals to 1. So the axis of symmetry of the moment is located at x equals to 1. Then we just draw it like this, then it is done. Now let's introduce the most important concept of this chapter, which is the Flexure formula. Consider a material under pure bending. It is bended by moment m. Then the material will be deformed like this. It will be very similar to a circular arc. The circular arc has a radius of curvature ρ. The Flexure formula will show the linear distribution of axial stress inside the beam. Consider a piece of material with the original length L being bent in a shape of circular arc. The circular arc has a radius of curvature ρ. For this piece of material, some portion of this material is compressed, while some portion of the material is being elongated. As you can see, the length of this arc must be smaller than the length of this arc. That means at some position of the material is compressed, while at another position of the material, say here, the material could be elongated. Actually, for a piece of material under the pure bending, there must be a neutral plane, which means no matter how you bend this material, on this neutral plane, the length is still the original length L. And this is the boundary of the compressed region and the elongated region. On this neutral plane, there is no axial strain, while above the neutral plane, if the material is bent like this, then this part will be compressed, while the lower part will be in tension because it is elongated. It is longer than the arc length of the neutral plane. Actually, if we observe the cross-section of the material, we can see that the neutral plane is like this. At this moment, we have no idea about where is the neutral plane, what is the properties of the neutral plane. So let's derive the formula one by one. Set y equals to 0 at the neutral plane. That is, we put the origin on the neutral plane, then at this neutral plane, y equals to 0. If we set the radius of curvature is the distance from center of the curvature to the neutral plane. The original length of the material, which is the length of the neutral plane, is given by L equals to ρ theta, where theta is the angle subtended by the center as well as the end of the material. Then the length at different position of the material, say y. If y is positive, that means we are talking about the material which is in the compressive region. If we say it is y, okay. The length at y is given by L prime equals to ρ minus y times theta. That is, the distance from center of the curvature to any position y is given by ρ minus y. So this is ρ minus y. So the length at any position y is given by L prime equals to ρ minus y times theta. Still remember our axial strain definition, which is epsilon x equals to the change of length divided by the original length. The change of length is given by L prime minus L divided by L, which equals to ρ minus y theta minus ρ theta divided by ρ theta. The answer is minus y divided by ρ. Consequently, we can say the axial strain epsilon x at any position y inside the piece of material is given by negative y divided by ρ. Just now we said that epsilon equals to minus y divided by ρ. That means the axial strain is linear proportional to y. That is, there is linear distribution of axial stress across the y direction. Now let's consider the force equilibrium on the cross-section. On the cross-section, for a very tiny differential area element dA, there will be direct stress sigma. The summation of sigma dA will be the force acting on the cross-section. However, we know that we are talking about statics. That is, we don't want any net force acting on the cross-section. That means the summation of sigma dA equals to 0. Well, what is sigma? It is given by E epsilon, which is the Young's modulus, times the axial strain. Then we substitute this one into this equation and take out the constants such that we can get this result. From here, we know that the double integral of y dA equals to 0. You might feel very familiar with this notation because we did it in tutorial 0. It means the first moment of inertia equals to 0, which means the neutral axis passes through the centroid of the cross-section. It is an extremely important result that you should know. An interesting observation is that the neutral axis does not necessarily lie in the middle. For example, for a trapezoid, the neutral axis is shifted downward. It does not lie in the middle of the y direction, but it will pass through the centroid, which is shifted downward. For this trapezoidal cross-section, we construct y-z coordinate plane. Now let's relate our derivation to the moment. Try to express the moment m in terms of axial stress sigma and position for neutral axis y. Consider a differential area dA, which has an axial stress sigma. It is located at position y from the neutral plane. The differential moment generated by this differential area is given by dm equals to y times sigma times dA. Notice that there is also a negative sign because in case y is positive, then it will generate a negative moment. That is, for this differential area element located at position y, if the sigma is positive, then it is a force like this. But we know for this moment, it is actually negative, as what we defined previously. That is, we must put a negative sign in front of it. Since we know that sigma equals to E epsilon equals to minus EY divided by rho, then we substitute the stuff into it to get dm equals to E divided by rho times y squared dA. We integrate both sides to get m equals to E divided by rho, since they are constants, times to the integral of y squared dA. As we introduced in tutorial 0, it is just the second moment of inertia with respect to z-axis. However, in the later examples of this tutorial, I will write it in IXX because it is rather convenient to set this axis to be x, then we set the longitudinal direction to be z-axis. So bear in mind with that. So although here we say it is the second moment of inertia in z-axis, but later when I deal with the problems, I will adopt this axis to be x. Okay. So it is up to you whether to adopt z or x, but all in all, you just need to understand the underlying principles or the reason why you should do that, then it is okay no matter which notation you use. Now combine those results, we have m equals to EI divided by rho, but we know that we can express E in terms of sigma x divided by epsilon x, and the epsilon can be further expressed in minus y divided by rho. Then you can get this equation. Notice that it is very hard to get rho in practical applications, so we seldom take it into consideration. So we want to eliminate it by using other means. This is why we substitute E equals to this and epsilon x equals to this to get an alternative result. Finally, we rewrite the equation to get the Flexure formula, which is given by sigma x equals to negative of my divided by I. Before using this equation, please check that the cross-section is axially symmetric and the loading is 1D. In general case, the axial stress inside the bar over 2D and the asymmetric cross-section is given by this formula. It was taught in MECH 3650 aircraft structures. As you can see, if the cross-section is not axially symmetric, then Ixy is non-zero, then the whole expression will be rather complicated. Therefore, we require the cross-section to be axially symmetric. Actually, we can simplify this very complicated equation by using our assumptions before. First, given that it is 1D loading, that is, my equals to 0, but you know this piece equals to 0 means that the whole piece equals to 0. Besides, Ixy equals to 0, that means this is 0, this is 0. Finally, you cancel out Iyy, then you will have only minus mxy divided by ixx remaining. So this is why the two assumptions are so important. Next is talking about the centroid finding technique. So in the tutorial 0, we introduced the first moment of inertia. the criterion of checking is given by qx equals to 0 or qy equals to 0. That means if you want to verify that a point is a centroid of a cross-section, then you can check whether those two criterion are satisfied. If not, then that point is not a centroid. To find the centroid, at the first glance, we know nothing about where the centroid is. That means we cannot set up the x and the y coordinate system. Instead, we try to construct a x prime and a y prime coordinate system at the boundary of the shape such that we can find it by using some integration method or summation method. For an arbitrary region, we temporarily define x prime y prime coordinate system at its edge. For example, this isosceles triangle, we set up x prime and y prime coordinate system here. Next, we try to compute the average of x or average of y based on this temporarily defined coordinate system by finding the first moment of inertia under this x prime y prime system first, then divide by its area to get the average value of x. That is, average value of x equals to the first moment of inertia divided by the total area. The same for average of y, the first moment of inertia divided by the total area. Now let's deal with an example of aircraft structures. It is actually a problem comes from MECH 3650 aircraft structures. I simplify this problem such that it is suitable for you to deal with. A thin wall can deliver with walls of constant thickness T has the cross-section shown in the figure. It is loaded by a vertically upward force W at the tip and a vertical downward force 2W at the midsection. Both forces acting through the shear center, which means there is no torsional effect in this beam. You are required to mathematically show that the centroid of the cross-section lies in the middle of the enclosed rectangle, as well as find the second moment of inertia, Ixx, Iyy, and Ixy of this cross-section. You need to determine and sketch the distribution of direct stress along the length of the beam for the points 2 and 3 of the cross-section. Notice that here we denote axial stress by using sigma C instead of sigma X, because we have a lot of sectional properties needed to be dealt with. Besides, ignore relatively very small terms for ease of calculation. Suppose t is very small in comparison to d. Firstly, let's show that the centroid of the cross-section lies in the middle. Firstly, we suppose we don't know where is the x and y coordinate system. We don't know where the centroid is. Therefore, we set up the x prime and the y prime coordinate system such that we can find the first moment of inertia of this cross-section first. Since it is a composite cross-section, we can just express the first moment of inertia in terms of the summation form. So the first moment of inertia about the y prime axis is given by the first moment of inertia of 1, 2, the first moment of inertia of 3, 4, the first moment of inertia of 2, 4, and the first moment of inertia of 1, 3. Then we substitute the average of x of 1, 2 as well as the area into the formula. The average value of x is d over 4 for 1, 2, d over 4 for 3, 4, 0 for 2, 4, and the d over 2 for 1, 3. The area of 1, 2, and 3, 4 are both td divided by 2, where the area for 2, 4, and 1, 3 are both td. The first moment of inertia of this rectangular cross-section about the y prime axis is given by 3td squared divided by 4. Similarly, for the first moment of inertia about the x prime axis, it is given by 3td squared divided by 2. Consequently, the average value of x and y are found to be d over 4 and d over 2 respectively, where it is just the position of the centroid. That is, the centroid lies in the middle of the rectangular cross-section. Now let's find the second moment of inertia, Ixx, Iyy, and Ixy of the cross-section. For Ixx, it is the integral of y squared dA over the entire region A. It is 2 times I12 plus I13. It is because I12 equals to I34 and I13 equals to I24. For I12, it equals to t cubed because since we are talking about y squared dA, then we talk about the thickness, which is in the vertical direction, will be cubed, and its length is d divided by 2. So its moment of inertia about itself is given by t cubed times d divided by 2 divided by 12. Besides, the area of 1, 2 is td divided by 2, while the distance of 1, 2 from x-axis is given by d over 2. So by parallel axis theorem, we can find another term of moment of inertia about x-axis. For 1, 3 and 2, 4, they are rather similar. They are both td cubed divided by 12. Then we simplify and organize the terms to get this, but as what we mentioned, t is very small in comparison to d, therefore we can neglect this term to be 0. The final answer for moment of inertia of Ixx is 5td cubed divided by 12. For Iyy, it is rather similar, but in this case, we don't need to apply the parallel axis theorem for 1, 2 and 3, 4. Instead, we apply the parallel axis theorem for 1, 3 and 2, 4. For 1, 2, since it's talking about x squared dA, then this length is taken into consideration and to be cubed. Since it is d over 2, then we have d over 2 cubed here. Then we times t. Besides, for 1, 3, still compute the moment of inertia of itself. It is given by t cubed d divided by 12. However, by parallel axis theorem, there is another term, which is td divided by d over 4 squared, where d over 4 is the distance of 1, 3 to the y-axis, as shown here. Reorganizing the terms and simplify it to get this. Finally, since t is very small in comparison to d, then we neglect this term to get Iyy equals to 7td cubed divided by 48. For rectangular cross-section, for Ixy it is very simple, since the cross-section is thinward rectangular, which is axially symmetrical. That means the moment of inertia of xy dA over the entire region A equals to 0 by empirical manner. Now let's determine and sketch the distribution of direct stress along the length of the beam for different points. First of all, we determine the moment inside the spar. Consider this simplified schema, 2W force in the middle and a W at the tip. By statics, we can immediately find the reactions at A. There is a moment MA as well as a shear force VA. Then by statics, take the moment at point A gives MA plus 2W times L over 2. L over 2 is the arm of 2W, minus W times L. L is the arm of W. So eventually you will get the result, which means the moment at point A equals to 0. Besides, for the shear force, assume an upward shear force. Then we find the shear force at point A, which is the reaction at point A, equals to W. Now we try to cut this cross-section, and we keep the right section for analysis. The sign convention of right section is like this. We take the moment here, then we can compute mx as well as v. However, under the pure bending case, we don't need to find v because the direct stress inside the beam is just caused by m. Therefore, we just find the moment in terms of se. mx equals to wse because for the upward force w, it has an arm of L minus se, while for the 2W force, it has an arm of L divided by 2 minus se. Therefore, by writing the moment equilibrium equation, we can get mx equals to w times se. Next, we consider the right section located here. So now the 2W force is disappeared as we propagate along the z direction. Mx is given by W times L minus se, where L minus se is just the arm of the moment. Now we can express m in terms of se, and we apply the equation sigma equals to my divided by I. Then we can have this result. Now let's consider point 2. At point 2, y2 equals to d divided by 2. Then we substitute y equals to d over 2 into the equation to get this result. Then, as you can observe, all those stuff are just linear to se. Therefore, the stress distribution along the length of the beam will still be linear. Consequently, we try to find the stress in the midsection, which is minus 3WL divided by 5td squared. And then we connect those lines together to get the distribution of direct stress. For point 3, which is here, y3 equals to minus d over 2. Then you substitute into the equation to get this. Also, you find the direct stress in the midsection such that you can draw this distribution. Notice that when we substitute in the numbers, we also take this one into the consideration. So it is the original problem, comes from our homework in MECH 3650, Aircraft Structures. It is for your interest, and if you have time, you may want to try out this problem by adopting this advanced equation. Next, let's talk about design considerations. Similar to what we discussed in previous tutorials, the maximum allowable direct stress is given by the yield stress of the material divided by the safety factor. Besides, we also consider the cost of the material. Also, for our Flexure formula, sigma x equals to minus my divided by I, it can be also written to be minus m divided by s, where s equals to the moment of inertia divided by y, is so-called section modulus. It expresses the strength of the cross-section. Now let's deal with an interesting problem about popular culture. I am a fan of Running Man, so maybe some of you are also fans of Running Man, and I especially found a problem from a previous episode that you might want to solve for it. In the Running Man episode 216, Lee Kwang-soo tried to pass through this bridge, as shown in the figure. His right hand here, touching this bridge, exerts a distributed load of 400 Newton per meter, so his hand is here, okay? Assume his shoes and knees exerts 70 Newton and 500 Newton concentrated load on this bridge respectively. So his shoes here has a load of 70 Newtons, while his knee gives a 500 Newton load onto the bridge. Sketch the shear stress and moment diagram of this bridge from point A to B. Assume it is a simple beam. Well, firstly, we try to find the reactions at the two supports A and B. By considering the force and moment equilibrium, you can find PA equals to 382.95, PB equals to 367.05. Next, we need to consider the loading condition in each segment. Say, since it is a concentrated load, distributed load, right? So we try to divide the section into different segments such that we can analyze the load condition in it. Because in different position X, sometimes some forces is removed. Sometimes you have to neglect some forces from your analysis. Consider the first section for X from 0 to 600 millimeters. On this section, it's rather easy. We take the moment at this end. The moment is given by PA times X. The shear force is given by PA. For this section, it is rather easy to analyze. For 600 to 1000, the shear force is given by PA minus 70. The shear force is given by PA minus 70 newtons, while the moment is given by PAX minus 70 times x minus 600. So here is 600 and this is the x. The 70 Newton force will provide an arm of x minus 600, and for the force PA it will generate an arm of x. So consequently you can rewrite the moment and the shear force equation in those forms. Then you can find the moment at this position and this position as well. For 1000 to 1250 millimeters, which is this segment, so it is x. PA has an arm of x with respect to this end. The 70 Newton force has an arm of x minus 600, while the 500 Newton force will have an arm of x minus 1000. So you can find the moment equation like this. For shear force, it is just the force equilibrium. Eventually, you can find the shear force and the moment equation in this form. Actually, no matter how you find moment and the shear force, from left section or right section as you like, as long as you keep the correct sign convention, then you will get the correct answer. Now let's consider x from 1250 millimeters to 1700 millimeters. We adopt two methods to find the moment. One is the left section and another one is the right section. For the left section, the sign convention is like this. The shear force can be easily found by using this formula. But notice that in the original problem, here it is given by 400 Newton per meter. So this unit can be converted to millimeter one, which is 0.4 Newton per millimeter. So you can find the shear force, which is PA minus 70 minus 500 minus 0.4 times the length of this distributed load. Simplifying it, get 312.95 minus 0.4x newtons. For moment, it is also not easy to compute. First, the PA still generate an arm of x. The 70 Newton force will generate an arm of x minus 600. The 500 Newton force will generate an arm of x minus 1000. For the distributed load, the moment is a little bit complicated to compute, but it should be fine. First, the length of the distributed load is given by x minus 1250, and as we know, the moment center of this distributed load is located in the middle of it. Therefore, the arm generated will be 1/2 of x minus 1250. Then you can find the moment like this, and then you simplify it to get this result. However, it could be faster if we can consider the right section. So consider the right section and label the rest of the forces on this beam. Now you only have one distributed load, and there was no 70 Newton and 500 Newton load acting on it. Now the length of the distributed load is given by 700 minus x, and the arm generated by the distributed load is given by 1700 minus x divided by 2. At the same time, PB will generate a moment with arm 2200 minus x. Therefore, by combining all those informations, we can find the shear force and the moment equation by using the right section. So for the shear force, it is just the distributed load minus PB, which is 312.95 minus 0.4x. The result is exactly the same to the method 1. Similarly, for the moment, we also adopt the right section to compute it, and we expand this result. And this result is exactly the same to what we found by considering the left section. As you can see, considering the right section can simplify the problem a lot. So notice that you should always bear in mind with the sign convention. For the left section, the shear force is downward. For the right hand side, it is upward. So bear in mind with that. And similarly, for the last section, from 1700 mm to 2200 mm, from the left section, you can find it is very complicated computation. While if we just consider the right section, it will give you the same result. So there is no reason that we consider the left one instead of the right one. So always bear in mind that you should always keep the correct sign convention for the left and the right sections. So bear in mind, it is very important. Finally, we combine all our known results into consideration, the Vx for different sections, as well as the moment Mx for different sections. Also, we compute some boundary conditions, like what is the moment and the shear force at 600, 1000, 2050, 1700 and 2200. We compute all those boundary conditions such that we can sketch the shear force and the moment diagram. So the shear force and moment diagram is sketched in this way. Just now we deal with the shear and the bending moment diagram of this beam. Now let's concentrate on the impact of the sectional properties on the material performance. First, we will derive the centroid of an isosceles trapezoidal cross-section mathematically. The upper base A, lower base is B, and the height is h. The upper base is smaller than the lower base, so like this. Besides, we will consider to make this bridge by using the concrete, knowing that concrete has very different yield stress for tensile and compressive stresses. The tensile yield stress is 5 million pascals. The compressive yield stress is 40 million pascals. If we ignore the shear force inside it, let's find the minimum section modulus required under a safety factor of 2.5 and the minimum cross-sectional area required for a square section. The reason why I require 2.5 as the safety factor is that I don't know whether Kim Chong-gu will pass through this bridge just by stepping on it. Besides, due to the constraint of program budget, a PD, program director, suggests to make the cross-section trapezoidal to save the cost of the bridge. So they want to have the minimum usage of the material such that they can save money for building the bridge. Design a cross-section such that the use of material is minimized for a safety factor of 2.5. You want to design the bridge such that the minimum cross-sectional area is attained. You are also required to think of it. What other design considerations should be involved? Firstly, for isosceles trapezoid, it is significant that the average value of x is lying in the middle. For the average of y, we need to first construct the x prime and y prime coordinate systems such that we can find the first moment of inertia of this cross-section. First of all, let's find the moment of inertia of this triangular shape. For this triangle, dA is the region bounded by the line y equals to 0 as well as y equals to 2h divided by b minus a times x. So it is notated like this. It is the range of y, the lower and the upper limits of y, which is bounded by two lines. Besides, it is also significant that x is ranging from 0 to b minus a divided by 2. Consequently, you do the integration like this, and then you take out the constant, as well as further integrate x squared dx by using this upper and the lower limits. Then the integration shows that the first moment of inertia of this triangular shape is given by h squared times b minus a divided by 12. Finally, you consider the area of this tiny triangle. You found that the altitude of the centroid is given by h divided by 3. That means the average value of y for the triangular shape is h divided by 3. Then we combine the result of first moment of inertia of the triangle with the result of first moment of inertia of the rectangle. We assemble all those components together to get a complete trapezoid. The first moment of inertia of this trapezoid is given by the first moment of inertia of the triangle plus the first moment of inertia of the rectangular region, which is 2 times the average value of y of the triangle times the area of the triangle plus the average value of y of the rectangle times the area of the rectangle. Then you substitute all the stuff into it and do the simplification to get the first moment of inertia of the trapezoid, which is given by h squared times b plus 2a divided by 6. You also know the area of the trapezoid is given by h times a plus b divided by 2. Therefore, the centroid of the trapezoidal cross-section can be found by dividing the first moment of inertia by its area. It is given by h times 2a plus b divided by 3 times a plus b. Then we can find the centroid of the trapezoidal shape. Next, let's talk about the design consideration of the material, concrete. The yield stress for tensile and the compressive are very different. Therefore, we need to take the section modulus for tensile and compressive sides into consideration. From part A, we know that the maximum moment is 355 Nm, and if we are taking the safety factor of 2.5, then consider the tensile region. The allowable stress is given by the yield stress divided by the safety factor, which is 5 million Pascal divided by 2.5 equals to 2 million pascals. Therefore, you are going to find the section modulus by using those two conditions. By substituting the values into those two conditions, you will find the section modulus of the tensile side, which is negative 177500 mm3. So what is the moment of inertia of a square cross-section? It is given by I equals to d to the power 4 divided by 12, where d is the side length of the square. For this beam, since the maximum moment is acting somewhere on this beam, that means the beam will be deflected like this. Therefore, tensile side will be below the neutral axis, while compressive side is above the neutral axis. At the outmost point of the tensile side, y equals to minus d divided by 2. We solve for this equation, that is, we put the moment of inertia as well as the outmost value of y into the section modulus equation, and we solve for d. Therefore, D equals to 102.1 millimeters and the area is 10429 millimeters squared. In part C, we discussed the possibility of building this bridge by using a square cross-section. Now let's try to build this bridge by using trapezoidal cross-section. Due to the constraint of program budget, a PhD suggests to make this bridge trapezoidal to save the cost of the bridge. We can save the money by cutting some material down such that we can reduce the cost of the concrete. That is, we want to minimize our cross-section. To do this, first we consider the moment of inertia I of the trapezoidal region. The answer is this, because the steps of derivation is too complicated, so it is left to you as an exercise in the practice problem set. Next, consider the section modulus required for both compressive and tensile sides. Just now we found the section modulus required for the tensile side. So now let's find the section modulus of the compressive side. Notice that the yield stress of the compressive side is 40 MPa. And by using 40 MPa divided by 2.5, you will get the allowable stress, which is 16 MPa. Then the section modulus can be found to be 350 Nm divided by 16. Remember, since we're talking about the compressive side, that means the allowable stress as compressive, it is negative, so we put a negative sign here. Consequently, we will get the section modulus, which is 22187.5 mm3, which is positive. So now for compressive region, we have the section modulus should be greater than this value, while the tensile region, the section modulus should be less than this value. That is, we want the section modulus to have higher magnitude. That is, if we set the section modulus to be greater than this value, then that means the section modulus should have a magnitude which is greater than this. Similarly, for the negative section modulus, if I say I want this section modulus to be less than a negative number, that means I want this section modulus to have a magnitude which is greater than this one. This is how we can strengthen the cross-section properties. Now, we have to satisfy both conditions. We also want to minimize the area of the cross-section. Besides, according to this diagram, we know that HC plus HT equals to H. That is, the height of the compressive region plus the height of the tensile region equals to the height of the entire trapezoid. Since the critical section modulus required in tensile and the compressive regions are related by the 8 times relationship, to minimize the use of the material, suppose for this trapezoid it satisfies HC equals to 8HT, that is, the height of the compressive region is 8 times to that of the tensile region. However, it is impossible because the lowest centroid allowed for the trapezoid should be greater than h over 3. It is impossible to make the centroid to be lower than h over 3. That means if you say the centroid is located at h divided by 9, then I will say it is definitely impossible for a trapezoidal cross-section. Unless you change the shape of the cross-section, then it is impossible to do that. So we try to adopt the lowest value of the average value of y, lowest value of the altitude of the centroid, which is h divided by 3 for our further analysis. When we take the centroid to be h divided by 3, the trapezoid will become a triangle in this case. Then a equals to 0, and we do a lot of cancellations. 0, 0, 0. And finally, you will get Ixx simplified to be h cubed b divided by 36. For compressive region, the section modulus expressions can also be simplified, as well as the tensile region. Also, we know that a equals to ha plus b divided by 2, but in this time, a is 0. Therefore, it will become hb divided by 2. Let's consider the tensile region. Then we have this inequality, because the statement from the tensile region, which is this one, is stronger than that of the compressive region. We simplified our problem a lot, and finally we draw a conclusion that we are trying to minimize the area, which is given by hb divided by 2, by using the condition h squared b is greater than 2.13 times 10 to the power 6 millimeter cubed. However, it seems that we can make h to be infinitely large and make b tends to 0, such that the area of the cross-section tends to 0. So it is just the pure mathematics that we try to analyze how to minimize the area by using a given condition. We know h can be very large while b can be very small. So if we make h to be very large, then the area will tend to 0. It will be very, very small, but it is not a reasonable design. One reason is that if we only take the cross-sectional area into the consideration, that is, we try to make the area very small, then you will get a cross-section looks like this. You crazy? As an engineer, you design such a cross-section. Still remember that how Yi Guangsu passed through this bridge? He is just riding on this bridge. If you give him such a bridge, then yeah, tragedy happens, right? The sharp tip of the triangular cross-section will immediately kill him. Yeah, and somehow, even though you say, okay, you are able to ride on it, but somehow it could have another issue, which is the strength of the material in other directions, because when he is passing through the bridge, there could be some literal load. Not only the 1D loading, but also the literal load will occur. For example, in this direction, somehow caused by the friction, right? So in case there is such a load occur, then how can you ensure the safety with such a thin cross-section? Then it is another issue that you need to address. In another word, the minimal value of A, which is the minimal value of the upper base, would be necessary for a reasonable design. So in our practice problem set, there is a problem which is modified from this problem, and there will be a value of A given, and you can try that out. Let's do some quick summary. So first, we made a very quick review of basic structural analysis, including what is the roller support, what is the pin, what is the fixed wall, and what is the simple support. For the roller support, there is only vertical load. For a pin, the load can be decomposed into orthogonal components. For the fixed wall, there could be force able to be decomposed in orthogonal components, as well as a moment. For the simple support, there would be a vertical component, and sometimes the horizontal component will also occur when there is friction. We also describe the sign convention of beams. Positive means smile face, while negative means sad face. And for the sign convention of the shear force, you consider a stress element located in between them. Then you can apply your results here. And finally, you get the complete sign convention of moment and shear force. Besides, we also introduced how to draw the shear and the bending moment diagrams, as well as the Flexure formula. So those two formula are very important, but I think it will be given in the exam. Besides, we also did some centroid finding techniques. What is the average value of x, what is the average value of y, and how to compute the centroid of composite shape, how to set up the temporary x prime, y prime coordinate system. We also talked about the design considerations, what is the maximum allowable stress, as well as the section modulus concepts. We also did a very comprehensive problem regarding to those issues. In this tutorial, there are 4 exercises. For exercise 4.1 and 4.2, they are just fundamental stuff. Exercise 4.3 related to some aircraft structure stuff, and example 4.4 contains every single concept in this tutorial. After watching this tutorial, you should be able to repeat what I have did in the tutorial and do some self-test and try to finish the problems independently. The total mark in this tutorial is 190 marks, and you can refer to the following tables to estimate your grade in your final exam. Still, this estimation is just for reference, and you are responsible for your own study and your own performance in your final exam. You are also recommended to do our practice problem set. Finally, thanks for watching, and see you in the next week.